All right, so there we go. So we're going to do another example about how to calculate the deformation using Castiglianos. All right, so let me try to move the cable. All right, so imagine we have an L-shaped beam. That is clamped at one end and simply supported at the other end. So guys, something important here is that do we need this boundary condition for this beam to be able to be there by itself, to sustain itself? This condition here is not necessary, no? So it's just redundant. So this problem means that this one's going to have more unknowns than equations, than the three equations we can use from statics. Okay? So this is called a problem which is statically indeterminated, no? Meaning that we need to add the additional equation. Okay? So in this problem, we're going to have a force apply over here, P. Okay? We're going to have the number 1, 2, and 3. And I'm going to do it a bit symbolically at the beginning. We put values for the finite element at the end. The length of each one of the edges is L. Okay, and the question is to determine the horizontal deformation at point 2. Okay, so first thing, like always, to do some type of figure or free body diagram. So this, for this problem, we could simplify the figure. We can just do a line, another line for the beams. And now, how many constraints are you going to have at point 3? This can restrain on the, so if this is bent, you can have a moment, M3, and then on these nodes, I call this one as R3X, and this one will be R3Y. And this one here should have R1Y, R1X. Again, this is at the points 1, 2, and 3. And we have here the force P. Okay, so over here, just like as initially, is that how many unknowns we have? We have R1X, R1Y, R3X, R3Y, and M3. So that means 5 unknowns. And how many static equations can we get? Can get summation of forces on the X, summation of forces on the Y, and the moments about the Z. So that's will be 3 static equations let's say summation of forces on the X, summation of forces on the Y, and the summation of moments about the Z-axis, okay? So what does that mean? That this problem is statically indeterminate or undeterminate. It's, as I've seen both terms, so indeterminate okay? So that means that we need to follow the procedure, flip-point diagram, static equation, and we need to find additional equations. So in this case, what would be the additional equations? What should be here the deformation at point 1? Should be 0, no? So that would be the additional equation. We always find it from geometry, no? So the deformation geometry here will be 0, okay? So we know that in order to find the deformation, we're going to use the Castigliano's theorem. All right? So what type of energy is available? So let's go here, strain energy. Okay, so what's important over here for you is to realize is what type of deformation the structure is going to have. Okay, now that I had it more. Okay, so over here, to know what type of energy you have available, we need to see, if you look at this drawing, maybe it's easier. Let's break this into 2 beams. One, let's look at beam 1, 2. When the beam 1, 2 is subjected to the force P, what type of loading will be carried by load 1, 2? Will be an axial loading, no? Okay, so what is the axial strain energy? The axial strain energy was derived to be equal to 1/2 integral, if you remember, P squared. But what is resisting the axial force is EA, is the cross-section area. And then we add here DS, okay, I think for our derivation. So this is the axial strain energy. Axial term, okay? Now, beam 2, 3 will be subjected to what type of loading? Beam 2, 3 will be subjected to bending, no? So now we need to define what is the strain energy from bending was 1/2 integral is m squared divided this time is EI, which is the one resisting bending, no? I. And I think here we call this one again DS, or it might be DX, I don't remember, but DS. It doesn't matter. So this is the bending term. That is being introduced by beam 2, 3. Okay? So now we can find the deformation using Castigliano's theorem. So using Castigliano's seventh theorem, what do we have? Q at a certain point I is equal to the partial derivative of the strain energy by a force at that point. So in this case, we are lucky because do we have a force applied at the location where we need to find the deformation? Yes, so that means that in this case, we don't have to assume a dummy force, okay? So in this case, our Q will actually be our P. So we can have here, this will be equal to the integral of P over EA partial P. I'm still going to call it Q sub I, but it's really P as well. ds plus integral of M over EI partial M partial Q sub I ds. So again, this term will be deformation. So this is the total deformation, okay? At point 2, we have a deformation due to axial deformation for bending 1, 2, plus another deformation due to bending, no? Okay, so this over here, we have axial. This is going to be pushing on this one, and then bending of this one. So, hold on 1 second. All right. Way over here, the P, okay, will be the axial force on each. So P here is the axial force on each one of the beams. And M is the bending moment. Okay, so this again becomes one problem like from statics. So we need to find the axial and bending moments. So axial force and bending moments. And this is the tedious part. Okay, so let's look at the beam 1, 2. So what is the procedure from statics in order to find the bending moment force and the shear force or the actual, I mean, actually the same procedure to find the actual force, the shear force, and the bending moment. If we start from this point, what do you need to do? You need to make a cut so that the internal actions can become external, no? So let's say we make a cut somewhere between 1 and 2. So in that case, I do the figure. We make a cut over here. In this end, we have R1Y, R1X, M1, and I could plot it, but here we're really interested on P1. But if we needed to find the shear force, you can just do the shear force in that direction, no? Okay? But I don't want to put too much. And this is 0.1 over here, okay? Okay, so in order to find the axial force, you need to take summation of forces on the x direction. Which will give you what? P1 minus R1X equal to 0. So from here you can find that P1 will be equal to R1x, which makes sense, okay? The axial force resisted by this one needs to be equal to the reaction on the x direction at point 1. Now next, in order to find the moment M1, what do we need to do? This is statics, 100%. Summation of moments about the cut, and you need to define a direction for moments. Oops. So I always count counterclockwise. So the way I draw here the moment is going clockwise, so that means that it's negative, so it will be minus M1. And now what is the moment created by the reaction R1Y? So that will be going counterclockwise, will be plus R1Y times that distance over here. Let's call this one S, okay? So R1Y times S. Let's call it S1 since we're gonna have another one for the other beam, S1. Equal to 0. So this will give us that M1 needs to be equal to R1Y times S1. Okay, I'm gonna go to the next page. Now to do the other beam, beam 2, 3. Okay, so for beam 2, 3, now we need to do the same thing. The tells you need to make a cut every time they say discontinuity. So you need to make a cut before the force P2. Now you need to make a cut before 3, no? Okay? So if I plot it, it will look something like this. So I make the cut somewhere over here. Okay, so we know this is L. Now this will be S2. We have our force here applied. P. We are looking for P2. And we have the moment over here. And cut 2. Okay, this should be actually vertical, okay? And let's not forget here we're gonna have R1X, R1Y. So in order to find P2, what we need to do is summation of forces on the Y. Which will give you what? R1Y. What else do we have? minus P2, let me check, yeah, equal to 0. So this will give you that P2 is equal to R1Y. Now this one is going to be a bit more complex. In order to find the moment M2, we're going to take moments about the cut. Positive counterclockwise. So now again, what do we have? The moment M2, I did it clockwise, so it's going to be negative. What else is creating a moment about the cut? What about the force P? Is force P creating a moment? Yes, and that moment will be clockwise as well, so it should be negative, so it should be minus P. What would be the arm? S sub 2. But here we need to be careful. What about the reactions over here? Is R1Y creating a moment? Is also creating a moment about the cut counterclockwise. So this one will be now positive, so plus R1Y, and the arm is the full length of the beam 1, 2, which is L. Remember here we had 0.1, 0.2, okay, this should be here 0.3. And R1X is creating a moment on the clockwise direction, so it will be negative minus R1X, and now again, the arm should be S2. Okay, so from here you find that M2 will be equal to what? I'm going to combine these two terms, so minus P plus R1X times S2 plus R1Y times L. Okay, so let me do a little summary over here of results. Let's say here, can we do more? All right, so let's say here beam. So we have beam 1, 2 in permeable space and beam 2, 3 here. I don't know how much space we're going to need, but okay, so we're first going to look at the axial force, and then at the bending moment. So for the beam 1, 2, where is that page? So what was the value of the axial force? Is R1X, so it's R R1X, and the moment is R1Y times S1. Okay? From here, from this page. And now for the second one, we have it on the same page over here. So for P2, we have R1Y. And for the moment equation, we're going to have minus P plus R1X times S2 plus R1Y L. Okay. All right, so now we need to go back to the beginning. We know this problem is statically undetermined, okay? So we need to find the two additional equations. So to determine the additional two equations, to determine the additional two equations, geometrical boundary conditions must be considered. So in this case, I kind of mentioned it before, is that what do we know about? So you need to look at geometrical boundary conditions. Okay, so you could use 0.3, but we didn't find M3, no? Okay, so using what we have, we can look at 0.1, correct? So what should be the X deformation and the Y deformation at 0.1? This is simply supported, so it means it's 0, no? This is free to rotate, but it's not free to move on the X or the Y. So the additional two equations will be what? So we know that at this point here, at 0.1, this is simply supported, which means what? That means that the horizontal deformation must be 0, but at the same time, the vertical deformation should be 0 as well, no? So if you want, QV equals 0 would be our fourth equation. And QH equals 0 will become our fifth equation. So that means now that after solving this, we should have 5 equations with 5 unknowns. I'm going to stop here in a second. Is that clear? This is important, okay? This step is critical, okay? All right. So now, what do we need to do? We need to solve QV equals 0, QH equals 0. What is the equation we're going to use in order to find the deformation? It's going to be Castigliano's equation, okay? So, page 91, there's no way we're going to finish this problem. So we'll finish next time, but I will just link or the copy paste those two videos together. So let's do the first one. Q, we have H of E, Q vertical equal to 0. All right, so let's look at the elements over here. So we have so the first one will be what? Let me write the general equation and then we'll do one by one. So Q vertical, we know the total deformation. There should be some terms due to axial, some terms due to bending, okay? The general form will be P sub I to know which member will go over EA partial P sub I ds. Let's leave this blank because I'm going to ask you what we need to put there. Plus partial of M sub I over EI we have here another force. So where is the previous page? What is the force at 1 that will create the vertical deformation? Vertical is in direction. So what is the force that will create for this member at point 1? The deformation. Remember, when you calculate the deformation here at a point, you need to find a force being applied at the same point, no? So what is the force on the vertical direction applied at point 1? Is R sub 1 y, no? So when you take the partial derivatives over here, this should be in function of partial R sub 1 y, partial R sub 1 y. Remember that you need a force being applied at the location of the deformation. Okay. So now, if we do the first term, what should it be? So for the first term, we will have okay, so we do the first term. What should be this? We know the force should be for the axial direction should be R1x, no? So we have here R1x over EA. Now, if we go to the table we had before, which is on the page I had, R1x is equal to what? So we had, okay, so is R1x, sorry, P1, sorry, is here, P1 here is equal to R1x, no? So now if you take the partial derivative of P1, which is R1x, with respect to R1y, that should be equal to what? Equal to what? 0, no? Okay, so now this should be here, if you want, partial of R1x with respect to, it's not really R1x, it's really P1. P1 with respect to R1y. This is 0 because P1 is equal to R1x. So this is 0. And you say this will be ds1 if you want, okay? ds1. You want to be accurate. But now we need to do the same thing for the second force. So it will be plus partial of. Now, what is P2? P2 is R1y, no? So here we'll have R1y over EA times partial of P2. So this is really P1, this is P2, okay? This is R1x, and we derive this with respect to R1y. What is P2? P2 is equal to R1y, no? Yeah? So then this term, what should be the derivative of this term? Should be 1. Okay, and this will be ds2. So in here, we took care of what would be the deformation due to P1 in member 1, 2 plus member 2, 3, no? So one is S1, one is S2. Now we need to look about the bending. So we do exactly the same thing. You need to look at this table. That's why I did it. So you need to look at this table. I know it's going to be, yeah, that might help. So now this will give you what? Plus integral of M1. What is M1 equal to? R1y times S1 divided by EI. So I'm going to stop putting because this is being too many details. M1. Now we need to take the partial of M1 again with respect to the same thing, which is what? Partial of R1y. So what was M1? M1 is R1y times S1. So you take the derivative of that, what will you get? S1. And this should be times ds1. Okay? Now we do the last term plus, so that one is going to be the long one. Hopefully I can put it on whatever is left. Now should be this, what? M2, which is the long one, which is equal to what? M2 is equal to, put a bracket, minus P plus R1X S2 plus R1L divided by EI oops, be careful here because this is R1YL, okay? This is the last term, times what? Partial of M2 with respect to R1Y, ds2. So what is partial? It's better if you look at this one. What is the partial of this with respect to R1Y? This should be just L, no? Okay? Okay, so I will stop over here one more line. Okay, so if we do this, this will give you R1 Y times L over EA plus, I'm going to factor out the EI over here to make it a little bit faster. EI, so this will give you R 1Y Y L cubed divided by 3 minus P L cubed divided by 2 minus R1X L cubed divided by 2 plus R1Y L cubed and this must be equal to 0. Okay, so I will stop over here, but next time we finish the video and I will put them together, okay? All right, so more, stop recording. Okay, guys, so last time I think we forgot, or I forgot to start the recording of this problem, so I'm not gonna rewrite it, but I'm just gonna mention it very quick. So this is the L beam, and this is where we stop. Okay, so what happened is that then what I did to go from here to here is that in order to simplify all the algebra, I use Maple and let's see. Here we go. So basically here, you see the only thing I'm doing is putting the values for on each one of the members. So basically, I'm just putting the values in this table. So we know P on each one of the members, 1, 2, 2, 3, and M, M1, M2 on the member M2. So this will be 1, here 1, 2, 2, and this will be 2, 2, 3. So it will be M1, M2, P1, P2, okay? All right, so if we go to the Maple file, that's basically what I have. So that now we know we can rewrite this expression here, okay? The way we obtain this one, I just rewrite it here in Maple, so you can do the integration. See P1 over EA partial of P1 with respect to R1Y, because that's the force going on the vertical direction at point 1. Okay, remember, this is the vertical deformation at point 1. And then for the horizontal will be R1X, okay? So we go back over here. So same thing for the second term. Same thing for now for the moments. And there we go. So we do this, and you see that I obtain this equation here that I call equation 4, okay? So that equation 4 here is actually the one I rewrote right over here, okay? Now we just redo the same thing in order to find the horizontal displacement at point 1, which is this one here. Now we need to take the partial derivative with respect to R1X. So that's what we have here on this equation is the same expression, but just this is R1X, okay? And this expression comes straight from the Maple code. So horizontal, we get this one here. That should be the same as that one over here. And that should be our equation 5. Okay. So the reason I call them equation 4 and 5, because I did not put them, but the equation 1, 2, and 3 should be what? Summation of forces on the X. And so what should be the equation of forces on the X if I needed to write it down? It would be what? R3X plus R1X plus P, okay? The summation of force on the Y will be R3Y per R1Y. And then the summation of moments, you need to select a point. So let's say we take it about 0.3, will be M3 plus P times minus P times L plus 31Y L minus 31X L, okay? But you can write them down, but we don't need them because we don't need to determine either R3X, R3Y, or M3. So basically what happened here is that at this point we have the 5 equations, 5 unknowns, but we only need to solve for R1x and R1y. So we only need these 2 equations, okay? So once we solve, you get this complicated equation. That's why we use Maple. And this is done over here. See equation 4, equation 5. Now I just put solve these 2 equations, and I get here the 2 expressions that I wrote over here. I think I just changed the order, but PL squared, there should be 18 PL squared EI. And yeah, you see 18 PL squared EI. Then another thing I mentioned during the notes but not on the video is that this is EA. Remember, this is E times A, okay? So this is not one variable. This is E times the area. This is E times the area. This is E times the moment of inertia, okay, for this term. All right. So now that we know R1x and R1y, so if you remember, let's look at the Maple file. We had all the values of the P1, P2 in function of R1x, R1y, M1 in function of R1y, and this one R1x, R1y. So that means now that we can have these expressions here will not be these ones anymore because we know the value of R1x, R1y. So if we substitute, this would be the new expression for P1, P2, M1, and M2, okay? So now we can find the deformation at point 2. Okay, so deformation at point 2 will be what? The horizontal deformation at point 2 would be with respect to which force? P. So basically, I will write the same expression as before, but this time with respect to P, 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 and then the moments P and P, okay? So beam 1, 2, 2, 3, 1, 2, 2, 3. And if you do the MATLAB, the Maple, sorry, so they will take a while to do it by hand, but I use here Maple. I remember S1 is 0 to L, S2 is 0 to L, so you integrate, you see this ugly expression, but magically you can just type simplify Q2, and you end up with this relation for the deformation, for the horizontal deformation at point 2. Which is given over here, okay? So to give some meaning to this, I just considered the same data as for the truss, I think the same properties. So 200 gigapascals, cross-sectional area of 400, L 1 meter. So we need to be careful here because we're mixing units. 100 kilonewtons of force, EA 80, and this is 2546. These values actually come from the final element model. If you substitute in that equation, you get that the deformation is about 0.01249 meters. Okay, so on the next video, I do the validation of this result with the final element, and that video will also be posted. All right, thank you for your attention.